Picture an open box with a heavy padlock hanging off it, and you place a stack of these boxes on a public table for the whole town to use. Anyone can take a box, drop a secret node inside, snap the padlock shut, and walk away. Once it clicks closed, not even the person who locked it can open it again. Only you, sitting at home, hold the one little key that springs that lock. The clever part is mixing two paints, say blue and yellow, is effortless, but staring at the green result and figuring out the exact two shades that went in is almost impossible. That one-way difficulty is the whole secret behind RSA encryption. Symmetric encryption needs both sides to already share a secret key, which is a chicken and egg problem on a network full of strangers. In 1977, Rivest, Shamir, and Adelman solved it with a scheme where the encrypting key can be fully public and only the decrypting key stays secret. RSA is asymmetric encryption built on modular arithmetic. The security comes from the integer factorization problem. Given a number that is the product of two large primes, no efficient algorithm can recover those primes. Your public key holds that product, and your private key holds the secret derived from the primes themselves. Pick two large random prime numbers, P and Q, each typically 1024 bits, so their product is a 2048-bit number. Multiply them to get the modulus n equals P times Q, which becomes part of both keys and is safe to publish. Compute Euler's totient, which for two primes is P-1 times Q-1, counting numbers below n that share no factor with it. Choose a public exponent E, commonly 65,537, that shares no common factor with the totient, and the pair n and E is your public key. Compute the private exponent D as the modular inverse of E with respect to the totient, meaning E times D leaves remainder 1 when divided by the totient. To encrypt a number M, raise it to the power E and take the remainder mod n, giving the ciphertext C. To decrypt, raise C to the power D mod n, and the math guarantees you recover the original M exactly. In practice, RSA never encrypts your file directly. It encrypts a small random AES key, and AES encrypts the actual data, because RSA is far too slow for bulk. With tiny numbers you can see it work. Let P be 61 and Q be 53, so N is 3233 and the totient is 3120. Pick E as 17, and D works out to 2753. Encrypting the message 65 gives 65 to the 17th power mod 3233, which is 2790. Decrypting 2790 to the 2753rd power mod 3233 returns exactly 65. Real RSA does this with numbers hundreds of digits long. A frequent error is believing RSA encrypts whole documents. It encrypts only short data, almost always a symmetric key, because a 2048-bit operation can handle barely 245 bytes and is thousands of times slower than AES. Another misconception is that a longer key is the only thing keeping you safe. Implementation matters just as much. Textbook RSA without padding like OAP is breakable, so real systems always pad the message first. Like those open padlocks anyone can snap shut, but only your home key can open, RSA builds two keys from two secret primes. Lets anyone encrypt with the public exponent, and lets only you decrypt with the private exponent, all protected by the impossibility of factoring a 2048-bit number. I unpack one piece of real cryptography every day, so subscribe to TechWithJoel. Why is 65,537 the almost universal choice for the public exponent E? Tell me what makes it special in the comments. Subscribe to TechWithJoel.